This lesson is on graphing absolute value equations. We'll use the same process that we did in all of Module 1, where if we have a function f of x, then if we graph a new function as a transformation of f of x of the form a f of 1 over b x minus h plus k, the multiplier in front will affect vertical stretch and compression. B affects horizontal stretch and compression. H affects horizontal shift. And K affects vertical shift. These are true for all functions. Today we're just going to focus on absolute value equations, but all these same properties that we learned in Module 1 will work with absolute value equations as well. So in example A, y equals absolute value of x minus 3 plus 2. The 3, h is 3, so that causes a shift right 3, and the plus 2 at the end is the k. K equals 2, so that's going to cause a vertical shift up 2. So we'll start with our parent function, which is just an absolute value graph. So y equals absolute value of x, our parent function. Absolute value of 1 is 1, absolute value of 2 is 2, absolute value of 3 is 3, absolute value of 4 is 4, absolute value of 0 is 0, absolute value of negative 1 is positive 1, absolute value of negative 2 is positive 2, absolute value of negative 3 is positive 3, and so on. So the parent function is just the same v that we've always gotten when we've graphed an absolute value function. Now we're going to take that parent graph and shift it right 3 and up 2. So take every single point that I just graphed and move them right 3 and up 2. So this point, right 3 and up 2 ends up here. This point, right 3, up 2. 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 And this point, right 3, up 2. So we see we get the same v, but the entire v has been shifted right 3 and up 2. So the blue graph is the graph that we're looking for. For example, B, the 2 in front is a multiplier which causes a vertical stretch by a factor of 2. And the minus 3 is k. K is negative 3, so that's going to move it down 3. Okay, so we'll start with our parent function again. And we're going to move every point on that graph. Actually, first we're going to do the vertical stretch. So that means every y value is going to be multiplied by 2 since a is 2. And so 0 is going to stay where it normally would stay. 0 times 0 is 0. This point has a y value of 1. So when we multiply it by 2, it gives us a y value of 2. This point has a y value of 2, so that's now going to be a y value of 4. So all these points are going to be stretched upward, multiplying the y value by 2. This point has a y value of 1, so it stretches up to 2. This y value is 2, so it stretches up to 4, and so on. And so now our parent function with a vertical stretch would look like this. And now we're going to take all the points on that graph and shift them down 3. So this point down 3 is here. 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 Oh, sorry, this point down 3 is here. This point down 3 is here. And so our final graph looks like this. So notice that on the parent graph, the slopes of a normal absolute value graph, if we just look over here at the side of a normal absolute value graph, the slopes here are all 1. And the slopes here are all -1. So what the multiplier of 2 does is it causes our new graph to have a slope here. The slope is 2. And here the slope is now -2. So since this is sort of a linear graph, the multiplier, when a equals 2, that's going to cause our slopes to now become 2 and -2. So I'd like you to go ahead and try example C. So pause your video, try example C, and then press play again when you're ready to see the solution. So as always, we start with our parent function. With slopes of -1 and +1. The multiplier of 3 causes a vertical stretch of 3. So the point at 0, 0 stays there. This point, which has a y value of 1, now stretches up to 3 because we multiply the y value by 3. This point has a y value of 2, so when we multiply by 3, it now becomes 6. This point has a y value of 1, becomes 3. This point has a y value of 2, becomes 6. So we see the same thing again. The multiplier of 3 in front causes our slopes now on our function to become, where they would normally be +1 and -1, become +3 and -3. Now we need to shift it. This would be h equals -2, because remember it's x minus h. And so h is -2 and k is +1. And so that means we're going to move it left 2 and up 1. So every single point on that last V that I graphed is going to move left 2 and up 1. So I'll start with this point at the origin, move it left 2 and up 1. This point moves left 2 and up 1. This point moves left 2 and up 1. This point moves left 2 and up 1. And this point moves left 2 and up 1. And so we see now that our final graph looks like this. So the blue graph is our final graph. Go ahead and pause your video again. Try example D and press play when you're ready to see the solution. Start with our parent graph. And as you've seen in the last two examples, the last three examples actually, we always deal with the stretch and compression first and then do our shifting last. And so when we now multiply our y values by -1/2, the origin still stays where it is because a y value of 0 times -1/2 is still 0. This point has a y value of 1, and so now it's going to be -1/2. This point has a y value of 2, so now it becomes -1. This point has a y value of 3, becomes -1.5. This point has a y value of 4, becomes -2. This point has a y value of 1, becomes -1/2. This point has a y value of 2, becomes -1. This point has a y value of 4, becomes -2. And so now we see that when we apply the reflection and the compression of a factor of 1/2, we get that graph. Now we're ready to shift it right 1 and down 4. So our final graph then, if I move every one of those points right 1 and down 4, this point right 1, or sorry, this point right 1 down 4, this point right 1 down 4, this point right 1 down 4, oh, sorry, I didn't move that one, right 1. Right 1 down 1, 2, 3, 4. This point, right 1, 1, 2, 3, 4. This point, right 1 down 1, 2, 3, 4. This point, right 1 down 1, 2, 3, 4. This point, right 1, 1, 2, 3, 4. So I didn't move all the points, but you get the idea just by plotting a few of the points what the graph looks like. And that is our final example for graphing transformations of absolute value functions.